Hey everybody, welcome back to another video. Today we're going to be talking about the thalamus, the medial geniculate body, and their significance and importance in tinnitus. Now, what is the thalamus? The thalamus is a principal subcortical relay for almost all sensory modalities that includes auditory, visual, somatosensory, and gustatory, prior to their projection to their respective primary cortical areas. Cortical means relating to the cerebral cortex. The cerebral cortex is the brain's outer layer, which is involved in higher functions like thinking, perception, and voluntary actions. Subcortical refers to structures beneath the cortex or beneath the surface of the brain. In other words, the thalamus, basal ganglia, they control emotions, automatic functions, coordination, etc., etc. Now, the thalamus is topographically divided or subdivided into many different nuclei, each with distinct cortical and subcortical connections. Now, for those who don't know, nuclei are clusters of neurons or nerve cells that work together to perform specific functions. For example, the dorsal and ventral cochlear nuclei are very good examples of nuclei. They are indeed clusters of neurons in the brainstem that process auditory information from the cochlea before sending it to higher auditory centers. And by topographically, I mean arranged or organized based on the physical layout or their structures in the area. In the brain, it refers to how specific regions correspond to specific functions in an ordered way, kind of like a map. If you guys remember from my previous videos, I also mentioned that the cochlea is also topographically organized, which means specific groups of hair cells in specific parts of the cochlea respond to specific frequencies, passing them on to specific auditory nerve fibers. This is also known as tonotopic organization, which is a specific type of topographic organization. Now, back to the thalamus. The thalamus not only channels and refines ascending inputs, like from the auditory nerve fibers through the cochlear nuclei, then the inferior colliculus, but it also is subject to continuous top-down modulation from the cortex. In particular, corticothalamic projections can either enhance or suppress incoming signals through local synaptic mechanisms, making the thalamus an integral gatekeeper for perceptual processing. Now, what are the major groupings of thalamic nuclei? The first type are relay nuclei, which are the lateral geniculate nucleus, LGN, for vision, the medial geniculate body that you guys might recognize for auditory input, and the ventro-posterolateral or ventral posteromedial nuclei, VPL or VPM, for somatosensory input and taste. Now, the next type of nuclei are association nuclei, or the pulvinar or lateral dorsal nucleus, which are involved in integrating multisensory and higher-level cognitive processes. Now, last but not least, the reticular thalamic nucleus, which is a thin GABAergic shell or group of neurons that surrounds the thalamus, which is critical for regulating how signals transition through the thalamic relay centers. It is also known as the RTN, and the RTN's inhibition controls whether specific frequency or amplitude-coded information proceeds to the cortex, making it extremely important in tinnitus perception. Now, let's talk about the medial geniculate body, or the MGB. Now, the MGB represents the primary auditory relay nucleus within the thalamus. It receives input mainly from the inferior colliculus of the midbrain and projects to primary and secondary auditory cortices. Everybody knows what the auditory cortex is in the brain. Now, alongside feed-forward auditory projections, which would be from the auditory nerve fiber to the cochlear nuclei to the inferior colliculus, the MGB receives very robust descending inputs from the auditory cortex and reticular thalamic nucleus, which enables precise feedback control. The MGB is divided into several subdivisions. Before I tell you about these divisions, here's a little graph on how to understand which positioning the dorsal, ventral, rostral, and caudal are. Take a look at this graph and keep it in mind. Now, the ventral division is characterized by strict tonotopic organization, projecting predominantly to the primary auditory cortex. Neurons here convey sharply tuned frequency-specific data under typical conditions. Now, the dorsal division of the medial geniculate body is less strictly tonotopic, often considered a higher order or associative sector that can integrate multimodal or limbic inputs, sometimes contributing to the affective or attentional components of sound perception. Now, the medial division is quite heterogeneous in function, meaning it's very diverse in function, and it is capable of integrating or modulating auditory information based on behavioral context, and it has connections to broader limbic circuits. Now, if you're wondering what the limbic system is, yes, the medial geniculate body is indirectly connected to the limbic system. It communicates with areas like the amygdala and other limbic structures, and it links auditory information to emotional responses like fear, threat detection, or stress levels, for example. These connections help integrate sound with emotional and memory-related processes. Now, before any Jastrabothians start screaming, "Oh, limbic system, medial geniculate body, that means anxiety can worsen tinnitus." No, this is not correct. Anxiety does not directly cause thalamic dysfunction. However, dysregulation in the thalamus can interact with anxiety-related processes because of its connections to the limbic system. But while anxiety primarily involves structures like the amygdala, prefrontal cortex, and hypothalamus, abnormal thalamic activity could contribute to sensory hypersensitivity or emotional dysregulation in some conditions. However, causation is very complex and not straightforward. Anxiety itself doesn't impair the thalamus. Instead, other factors like chronic stress or other neurochemical imbalances might affect thalamic function, and chronic stress can, not always, but can be caused partially by chronic anxiety. Now let's talk about synaptic architecture in the MGB. Now, in each MGB subdivision, which I just told you about, principal relay neurons, mostly glutamatergic thalamicortical projection cells, and local interneurons, GABAergic, orchestrate how auditory signals are processed. Principal neurons receive ascending excitatory drive from subcollicular structures and descending excitatory or modulatory drive from auditory cortical layers. Now, if anybody's confused about what I just said, by ascending excitatory drive from subclavicular structures, it means the MGB receives excitatory input from subclavicular structures, such as the inferior colliculus. And this input carries auditory information upwards to the cortex. And the descending excitatory or modulatory input from auditory cortical layers means that the input, the thalamus or the MGB, also receives input from the auditory cortex. This input can be excitatory or modulatory. And in this context, modulatory doesn't necessarily mean inhibitory as well. It can involve changes in the gain, timing, or responsiveness of the thalamic neurons. And while inhibition could occur indirectly via cortical influence on inhibitory interneurons, the input from cortical layers is typically excitatory or fine-tunes the thalamic response. Now, the GABAergic neurons, which are typically inhibitory interneurons, whether intranuclear or originating in the reticular thalamic nucleus, control the timing, magnitude, and coherence of the firing in principal cells. This delicate interplay of excitation and inhibition is very important to the MGB's role as a selective amplifier or dampener of auditory signals. Now, if you guys have watched my previous videos, you might recognize a pattern here of the importance of excitatory and inhibitory balance. Principal neurons, which are also called fusiform cells in the dorsal cochlear nucleus, and inhibitory interneurons, like vertical cells or cartwheel cells in the dorsal cochlear nucleus, have a very fine excitatory and inhibitory balance, which is not exactly the same as how the principal and inhibitory interneurons perform in the medial geniculate body. But you can see how this excitatory and inhibitory balance is important not only in the cochlear nuclei, but also in the thalamus as well. Now let's talk a little bit about visual snow syndrome. Now, visual snow syndrome, for those of you who don't know, involves the persistent static or flickering noise across the visual field alongside other potential visual disturbances like after images, palinopsia, etc., etc. And while cortical hyperexcitability in the early visual cortex has been implicated, thalamic involvement may parallel what is observed in abnormal audition. In VSS, evidence suggests that altered function in the lateral geniculate nucleus and possibly pulvinar, similar to the MGB's role in gating auditory information, these visual thalamic relays can abnormally pass intrinsic or noise-like signals upwards if local inhibitory circuits or reticular nucleus input are disrupted. This phenomenon aligns with the concept of thalamic cortical dysrhythmia, in which oscillatory and synchronizing mechanisms in the thalamus fail to adequately suppress unwanted different noise. And by analogy, the MGB's dysfunction in tinnitus shares mechanisms or mechanistic similarities with LGN dysfunction in VSS, where gating deficits allow the internal noise to be perpetuated at the cortical level. Now, if we talk a little bit more about thalamic cortical dysrhythmia, both the lateral geniculate nucleus in the visual pathway and the medial geniculate body in the auditory pathway are obviously part of the thalamus. And disruptions in the thalamic cortical networks, like abnormal signaling or hyperactivity, could affect both of these sensory systems, leading to VSS via the LGN and tinnitus via the MGB. Now, obviously, visual snow and tinnitus involve hyperactivity or dysregulation in their respective cortices, the visual cortex for VSS and the auditory cortex for tinnitus. And since the brain's sensory systems are interconnected, dysfunction in one network could potentially influence other sensory modalities. Of course, imbalances in inhibitory neurotransmitters or excitatory neurotransmitters could dysregulate the sensory processing, of course, across multiple modalities. This is why I think that people who have visual snow syndrome might have more thalamical involvement than those who do not. As you know from my previous videos, all of these neural pathways are just, excuse me for my French, clusterfucks of ascending and descending feedback loops. More on visual snow later. I'm going to be making a separate video on that. Now let's talk about cellular and network determinants of thalamic gating mechanisms. Now, thalamic gating relies on a confluence of intrinsic membrane properties, local circuit interactions, and top-down or cortical-fugal synaptic influences, which basically means that thalamic gating depends on the combination of the thalamus's own properties, local neural connections, and signals coming from the higher brain areas. Now let's talk about intrinsic membrane properties of relay neurons. The T-type calcium channels. Now, the characteristic of thalamic relay cells, these channels enable low threshold spikes following a hyperpolarization. They allow for thalamic neurons to toggle between burst and tonic firing modes. A quick description: in the thalamus, burst firing is when neurons fire rapid bursts of signals, which is often used to detect new or important information. And tonic firing is a steady, regular pattern of signals used for continuous processing of sensory information. Okay, here is a post-recording commentary, actually, when I was trying to explain on the previous graph that PGN neurons are not actually related to the auditory pathway. The PGN, or the parageniculate nucleus, it modulates the visual processing near the lateral geniculate nucleus. So it's for visual processing. But a similar modulatory function in the auditory thalamus, that is the medial geniculate body, is carried out by the thalamic reticular nucleus, which we talked about previously. And interesting enough, the thalamic reticular nucleus is involved in modulating multiple sensory pathways, including visual, auditory, and even somatosensory systems. It does not belong exclusively to any one sensory modality. So the TRN, inhibitory GABAergic neurons, are connected to the lateral geniculate nucleus to regulate and fine-tune visual information that reaches the visual cortex. And it plays a very important role in processing by gating signals. And in the auditory pathway, the TRN neurons also interact with the medial geniculate body, modulating auditory information that goes to the auditory cortex. So potentially dysfunction in the thalamic reticular nucleus's inhibitory function could be the missing link between tinnitus, visual snow, migraines, and noxicusis. So I think that the thalamic reticular nucleus definitely needs way more research in its functionality and importance regarding these conditions. Now, the IH-HCN channels, also known as hyperpolarization activated and cyclic nucleotide gated channels, they depolarize neurons back towards threshold after hyperpolarization. And this influences rhythmic activity, baseline excitability, and gating thresholds. Now, if you all remember from my 5-HT video, the HCN channels can very well be modulated by 5-HT. So keep that in mind. I hope most of you made that connection by yourselves. Now, let's talk more about the reticular thalamic nucleus, or the RTN. Now, it is composed of GABAergic neurons wrapping around the dorsal thalamus. Now, it exerts inhibitory control over the relay nuclei, creating windows of excitability or suppression. And when RTN activity is high, it can strongly hyperpolarize NGB neurons, reducing their throughput to the cortex. Now, what does this sound like? That's right, cartwheel cells in the dorsal cochlear nucleus, strongly influencing the excitatory drive towards the higher regions like the inferior colliculus. You guys can see the pattern here of excitatory and inhibitory balance being very important. Just like the dorsal cochlear nucleus, where cartwheel and vertical inhibitory interneurons control the excitability and consequently how much excitatory drive is sent upwards, the RTN also does this. So when cartwheel cell activity is high, it can strongly hyperpolarize the principal neurons, or the fusiform cells. Just like when RTN activity is high, it can strongly hyperpolarize the MGB neurons. If you guys remember, hyperpolarization is when the membrane potential becomes way more negative than the resting membrane potential. So if you take a look at this graph right here, you can see that hyperpolarization is this strong dip below the resting state. And in this state, when the membrane potential is much more negative than the resting state, it is very difficult, if not impossible, for the neuron to fire another action potential, leading to an overall decrease in neuronal hyperexcitability. Now, spectral selectivity refers to how a system, or the auditory neurons, for example, responds to specific frequencies of sound, or the pitch aspect. It's about distinguishing what frequencies are present. And temporal selectivity refers to how the system responds to the timing or the rhythm of sound, the when. It's about distinguishing patterns over time, like detecting fast or slow changes in sound. Now, about corticothalamic feedback, descending projections from the auditory cortex, especially layers 5 and 6, synapse onto both thalamic relay neurons and RTN neurons. And cortical feedback can heighten or diminish responsiveness to certain frequencies or sound features, effectively tuning the MGB based on task relevance or attentional demands. And within normal physiological ranges, these factors maintain a balance that allows salient external auditory signals to pass while spontaneous or disorganized activity is filtered out. Thus, gating is not only passive, but a very highly dynamic mechanism. Now, let's talk a little bit more about tinnitus specifically and the neurophysiological interactions. As we know from my previous videos, tinnitus is a combination or the result of a combination of multitudes of factors that eventually leads to enough hypersynchronized neurons in the dorsal-cochlear nucleus to present their excitatory drive towards the higher regions, eventually being recognized as the thalamus as, something important or noise, and that's why we perceive it. And while peripheral acoustic trauma or different cochlear damage, they often do initiate this, or they are a precursor to this cascade leading to dorsal cochlear nucleus hyperactivity. It is the subsequent ascending and thalamic gating abnormalities that can also contribute to tinnitus entering conscious awareness. Now, about ascending synchrony from the dorsal cochlear nucleus. Now, in tinnitus, obviously, the fusiform cells display increased spontaneous firing and hypersynchrony, which forms a coherent subthreshold signal that ascends via the inferior colliculus. And if the MGB's normal inhibitory calibrations are compromised, for example, via dysregulation of GABAergic interneurons, or due to HCN channel dysfunction, for example, from 5-HT involvement, this synchronized activity can, as I mentioned before, become recognized as a valid auditory event. Now, again, not everybody has thalamic dysfunction. Tinnitus can definitely occur due to a very, very high level of hypersynchrony in the dorsal cochlear nucleus, where regardless of thalamic functionality, this still would be recognized as a valid auditory event. So don't be freaked out. Not everybody with tinnitus has decreased inhibitory calibrations in the MGB. Now, maladaptive plasticity within the inferior colliculus or the dorsal cochlear nucleus, combined with cortical feedback, can technically promote an abnormally high excitatory tone in the MGB relay neurons, and chronic states of heightened excitability reduce the activation threshold for projecting signals upwards, which basically locks or it effectively locks the system in a partial tonic mode that contributes or continuously relays these phantom inputs to the auditory cortex. Now, there can be an interaction with inflammatory or excitotoxic mechanisms, and while peripheral triggers like acoustic shock or local cochlear inflammation can be the precursor or maybe even the initiator of the problem, depending on how many cofactors the person has, including somatosensory, of course, the ongoing low-level neuroinflammation can propagate upwards to subcortical structures, which alters the receptor expression or local circuit function. And as we all know, migraines are also thought to be related to neuroinflammation. So people who enjoy Hamid Jalilian's work can keep that in mind, especially if we're talking about tinnitus with very high variability, or tinnitus that goes up and down really often. Now, more in depth about this, the inflammatory mediators can sensitize the D-type calcium or HCN channels, lowering the gating threshold and biasing thalamic relay cells towards pathological bursting or tonic firing. This enhances the probability that spontaneously firing neurons will achieve synchronous discharges that pass the MGB filter. Now, if we talk about top-down facilitation, or neutrality, the higher order cortical projections do not necessarily turn up the volume in everyone with tinnitus. In many cases, strong cortical inhibitory feedback might still suppress emergent phantom signals. And individual variability in cortical feedback, genetic factors affecting ion channels, and differences in reticular nucleus organization determine whether the MGB's gating will fail under otherwise similar or peripheral conditions. Now again, anxiety is not regarded as a direct driver of these mechanisms. Chronic anxiety states do not themselves cause the MGB or reticular thalamic circuits to degrade, gating performance. In clinical or experimental observations, individuals with similar DCN or inferior colliculus hyperactivity can have drastically different subjective tinnitus outcomes regarding their anxiety status. Therefore, while stress hormones and neuromodulators like cortisol can influence many neurobiological processes, there is not really any consistent evidence that anxiety itself, per se, worsens objective thalamic gating or the pathological synchronization that underlies tinnitus. I would actually say we have evidence from the community that anxiety itself does not modulate tinnitus. Maybe tinnitus perception, yes, if we're talking about habituation and sensitization, but objective volume of tinnitus, no. Stress or cortisol release and bruxism or grinding can affect, actually very significantly, tinnitus objectively. For example, aberrant somatosensory signals to the DCN through SP5 input, like during trigeminal nerve irritation, or a constant activation through grinding or bruxism. Yes, it can affect tinnitus, and stress or cortisol levels does also affect neurotransmitter function and can also further sensitize neurons. So these two factors can arise from anxiety, but this does not mean that anxiety itself directly causes objective, for example, worsening of tinnitus symptoms. Now let's talk a little bit about thalamic network oscillations. Now, in normal or pathophysiological states, the MGB and other thalamic nuclei can engage in specific oscillatory activities. For example, the alpha or beta band from 80 to 30 hertz oscillations often are related to wakeful states, attentional gating, or mild suppression of irrelevant sensory inputs. And the gamma band, or above 30 hertz oscillations, can signify heightened alertness or sensoromotor integration. Now, in pathological conditions, excessive gamma synchronization can drive or reinforce abnormal bursting in the MGB. And low-frequency oscillations from 1 to 4 hertz, which are observed in transitional states or under sedation, and abnormal presence of low oscillations in awake states can degrade temporal fidelity of gating, though these phenomena are more commonly studied in the context of sleep or anesthesia rather than tinnitus. Now, when the MGB aberrantly transitions to or remains in a tonic firing mode at a high gain due to diminished local or reticular inhibition, it allows ephemeral bursts of spontaneous activity from the midbrain, inferior colliculus, or DCN to pass unfiltered. The phenomenon of synchronal gamma activity across DCN IC-MGB circuits has been hypothesized to produce a sufficiently robust phantom tone, quote unquote, that the auditory cortex encodes as persistent noise, or tinnitus. Now, even in scenarios where individuals are not anxious, the gating deficits at the thalamus remain an intrinsic network problem rather than a state-based emotional or physiological phenomenon. Now, not all people, of course, even with dorsal cochlear nucleus hyperactivity, develop persistent tinnitus. Now, this intersubject variability is often, of course, explained by the robustness of thalamic inhibitory circuits or intrinsic interneurons and RTN. Genetically influenced expression or subunit composition of T-type calcium channels and other ion channels in relay neurons, the variation in cortical feedback strength or patterns, some individuals having more potent top-down suppression under these circumstances, or differences in how excitatory-inhibitory synergy reorganizes post-injury or inflammation. And also, of course, by somatosensory cofactors potentially increasing the synchronization in the dorsal cochlear nucleus, which of course leads to the thalamus recognizing this aberrant synchronous activity as sound rather than random spontaneous firing or disorganized neural noise in the auditory pathway. Now, of course, we know about the Susan Shore device, which decreases aberrant or hypersynchronization in the dorsal cochlear nucleus, which will, of course, lead to the thalamus not recognizing this synchrony as a significant auditory event. Will there potentially be therapies for the thalamus, or specifically the manipulation of the medial geniculate body microcircuits, like, for example, selectively boosting inhibitory neuronal function or modulating hyperactive relay neurons, or even bimodal or bisensory stimulation potentially here as well? I do see some promise here. I think that the thalamus does show potential for, targeting it as a potential area for future treatments. And while decreasing hypersynchrony in the auditory pathway could potentially be a solution for many people, I still think that this area should definitely be explored further, of course. And that's about it for today. And if you have any more questions about this, you can, of course, join my Discord server, where we will have scientific discussions.